So I don't have any presentation slide, but my name is Gaston and I work at AFRY as well, together with Hampus. And I've been working with data science for about 3.5 years now and started at AFRY in in August. And I have a background in engineering and mathematics from LTH, the engineering faculty at Lund University. And today I want to talk a bit about an old topic, which is my master thesis that I made at my time in LTH. So the title of this presentation is Surface Classification with Radar Data. And what this project was about was that we had this robotic lawnmower like that, and we mounted a radar sensor at the front of that lawnmower, pointing downwards. And as it went forward, we collected radar measurements from underlying surfaces. So we did that for a bunch of different materials. It was for grass and asphalt and soil and gravel, I think, and also tiled floor. And the idea was to be able to distinguish grass surfaces from other types of surfaces using machine learning and the data that we collected. And the reason we wanted to do that was, when you have these robotic lawnmowers, you have this wire installed around the boundaries of your yard, and the lawnmower relies on that wire to detect when it crosses the boundary. And it's quite cumbersome to install that wire, so if the lawnmower can detect the boundary itself, it would save a lot of time and complexity. Oh, and a fun fact as well. My middle name literally turns out to be Radar. So I know what I'm talking about. So before we go into the specifics of the project, I want to give you a brief background about radars in general, because I think it's quite a niche topic, and it's important to understand what the data means when you look at it and where it's derived from. So I will start with some radar basics. And radar stands for radio detection and ranging, and it's a technology that's used to detect whether there's a object or some target present in front of the radar as you point it towards some place, and also detecting what the distance is to that target. And there are different kinds of radars that work differently, and the one we used is called a pulsed radar. And I'm going to show a bit how a pulsed radar works, the very basic principles behind it. So I've made a small animation here, and that shows a radar and some target that's going to be detected. And then we're going to generate some data from this scene. So what's going to happen is that the radar has a transmitter and a receiver, and then it's going to transmit an electromagnetic pulse that travels through the air, reaches the target, and goes back to the radar's receiver. And then it's going to be, when it picks up that pulse, it's going to be able to detect the distance to that target. So there we go, let's fire off the pulse. And it's going to start traveling towards this airplane, and the receiver goes into listening mode. So it's constantly checking, has a pulse arrived yet? And it's trying to see whether the pulse has reached the receiver. Kind of like the child in the back of a car seat going like, over there yet, over there yet, over there yet. And then the parent says, no, no, until finally the pulse reaches. And yes, there we go. And we detect a peak in the response curve. So the cool thing here about this now is that the radar keeps track of the time it takes for the pulse to travel from the radar to the target and back to the radar again. So we know the time t here, and we also know that the pulse travels at the speed of light since it's electromagnetic radiation. And that way we can calculate using this simple equation the distance to the target. And the reason we divide by 2 here is that the time we measure here is the time it takes for the pulse to travel back and forth, but we're only interested in the one-way distance, so we compensate by dividing by 2 here. So we have the time here, but we could also substitute that for the distance in this axis. So we can think of it as either a time or a distance axis. So this is the simplest case, I would say, where we have one static target at some distance, and we get some response from that, which is a peak in the response curve. But of course, we could also have multiple targets. So we're going to look at another animation where we have 2 targets instead, and the pulse is going to be sent towards those and be reflected at different times and returning to the radar. And we're going to see what the response looks for that curve. So let's fire it up. So here we see one pulse reflected, and then we get 2 peaks like that. So one pulse is reflected earlier and returns to the receiver at time t1, and the other one at time t2. And of course, we can do the same thing as before. We just convert the times into a distance with this simple equation, and we see at what distance its objects are present. one thing we can note here is that the amplitude of this peak is larger than the second peak. And the reason for that is that as the transmitter sends out a pulse, it does so with a finite amount of energy. And as the pulse is transmitted, it's going to be spread out in like a semisphere from the radar in all directions. And the further away from the radar you go, this finite amount of energy is going to be distributed evenly around this, or not evenly, but it's going to be distributed around this area that's expanding as you move further away from the radar. And as we hit this target, the power hasn't been as spread out as when we hit this one. So when that echo returns, we're going to have more power in that response. And that's why this peak shows up as a bigger one. I think, was there anything else I was going to say about this? Yeah, I can also mention some radar terminology. So we have this graph here that's generated. And the way radar works is that it transmits a pulse, and then it goes into listening mode for a while. And when the listening mode is over, it transmits another pulse, and it keeps doing that, like transmitting and listening, transmitting, listening. And one of these iterations is called a radar sweep. So one sweep generates one of these graphs each. And now we're going to go a bit more into the project specifics. So the way we collected data is that we had this robotic lawnmower move across the surface like that. And as it moved along, it collected these sweeps one by one. And we stacked them over time like this. So now all of a sudden we have two time axes. We have one that we looked at before, which collects the sweep like that, and we visualize it. And then we have this other time axis where we stack the sweeps together one by one after each other. And it can get a bit confusing having two time axes. So in radar terminology, you often say that you have fast time here and you have slow time. But sometimes you also say that this axis can be called the range axis or the distance axis, since it's the times here can be easily converted into their corresponding distances. And having this data here, we can think about that as a two-dimensional matrix like this. So we have the slow time axis on one part and the fast time axis on the other one. And so this is pretty much the same type of same data, we just represent it in different ways. So the fast time is what we got from a sweep like this. So it's made super quickly. We send out a pulse and it's fractions of a second. It's really quick. And then the fast time here is when you have taken separate sweeps and stack them together like that. So that is going to depend on how often you sample. So if you take one sweep every second, then it's going to be 1 second between each step here. Whereas this one is a really, really short amount of time. So that's why we call it fast time and slow time. So this is the data that we have worked with. It's quite suitable that we have it in a two-dimensional matrix because it's suitable for machine learning, which we're going to apply on the data soon. I think it's. I'm going to go into some, on the next slide, I'm going to go into what we're actually doing with the data and some feature engineering. But do we have any questions about so far about what I've talked about? Or should we move along? Otherwise, we can just stop at any time and stop for questions. All right. So what you could do is that you have this two-dimensional matrix, and you could actually just take a neural network and plug this into that and label it if it's a grass surface or if it's a asphalt surface that you've measured on, and then train that and classify and probably get something out of it. But there's also more clever things you can do beforehand to prepare the data a bit better. So we've done some feature engineering in this work, and one of the things we did at first was that we realized that we could probably downsample the data a bit because we're measuring at some distance and then we measure slightly further than that from the radar sensor and so. So, I mean, if we look at one slice here, for instance, each of these corresponds to a distance from the radar sensor. So this line, for instance, the red one, would correspond to measurements made 14 centimeters away from the radar. And as we move along this line, that shows how the measurements vary over time as the lawnmower moves. So we can see that the amplitude changes as we move along when we look at 14 centimeters away. And looking at this one, for instance, maybe we see what it looks like 13 centimeters away from the radar. So we have a bunch of different time series like that. And I mean, if we would take all the data that we have and look at this red line, for instance, and take the slice slightly below that, then maybe we would look at a distance 14.05 centimeters away from the radar, and that would likely carry the same information almost exactly as this other one. So, I mean, looking at 14 centimeters away and 14.05, it's probably going to introduce redundant information. So what we decided to do is to downsample the data and just look at a few selected bins like this. And so we included that raw data but downsampled in the model as one feature. Another thing we did was also to treat these individual slices like that as time series. So the red line here would correspond to these points that varies over time for this particular range here. And since these are time series, we can use them to extract information from those. And we did experiment with a few different things, but the thing we found the most useful was looking at autocovariances. And I'm going to show in the next slide a bit why we did that and why it proved to be so useful. So we looked both at the autocovariance in how this sweep changed over time, but also we took the autocovariance in energy, and that means that we took each sweep and computed the energy within that. And we did that for every sweep and looked at how the energy changed over time as well, and had that as a feature. I can give a small side note as well I should mention, because the data I'm showing here is actually a bit simplified in reality, because a radar actually returns complex value data which contains information both about the phase and the amplitude, but here I'm only showing the amplitude part of the data to keep things simple, but there's more to it. There's a bigger picture that I decided to keep out of here. Okay, so this autocovariance feature was something that we had an idea about, or a gut feeling that it would be a useful feature. And the reason for that is that if we look at grass compared to, for instance, tiles, those different materials, and we want to distinguish those, grass is a really rough surface. It's lots of things going on as you move along it. It's very random, much randomness in it, and you can imagine if you're looking at some distance from the radar sensor as you move along in the grass, it's going to jump up and down a bit and be very sporadic and act in all sorts of ways as you move along it. So you get this kind of a jumpy pattern like that. But for a tile surface, for instance, no matter where you look, it's going to be flat and it's going to look the same. The reflection is going to be quite the same from wherever you're standing with the lawnmower when you make the measurements. So we would expect that we'd get a quite flat response curve like that as you move along the slow time axis. So looking at the autocovariance for a sequence like this, we should have a lower autocovariance for a time series that's randomly changing as we move along compared to one that's pretty much constant. So that's something we looked at, and it turned out that was the case when we made the estimates. So here we see some estimates for different underlying surfaces, and we see that the star one here, the tiles, turn out to have the highest autocovariances for different time lags as well. And I could mention that here a time lag of 1 and 2 and 3, for instance, means that we're comparing the covariances between samples that are, if it's a lag of 1, it's comparing the covariances of one sample, the sample for one sweep with the samples for the next sweep. And if it's a lag of 2, we would compare the 2 steps apart. And so the further you go away from each other, the less correlated they're going to be, and the autocovariance is going to drop. And specifically for grass, it seems to be, or it is significantly lower, and it decreases quite quickly as we move further away in the sweeps compared to the other materials such as tiles, which has the highest autocovariance. So that was the most useful feature that we found. Okay, so before we talk a little bit about modeling as well later on, we're going to look at our total features that we had. So we ended up with a feature set of 174 features, and that was comprised of, first of all, the sweep values that we looked at. We took these downsampling and selected 28 ranges that we looked at, and we did some averaging over time to reduce the noise. Then we also looked at autocovariance in the energy, which gave us 6 additional features, and also the autocovariance in range, which gave us 140 features in total. Okay, so another thing I want to highlight as well, which was quite cool, I think, is how we used PCA to kind of see whether it was going to be possible to distinguish the grass from the other surfaces. So the feature vectors now, we have 174 features and a bunch of samples. So we're basically working in a 174 dimensional space, and the question is, can we separate the grass samples from the other samples in this high dimensional space, which is of course hard to say when you can't see the samples because of the high dimensionality. So what we tried was to use principal component analysis to reduce the data set, to squeeze it down to just 2 dimensions, to see if it was possible to separate them. So PCA projects down data into a lower dimensional space in such a way that it maximizes the variance. So it tries to keep as much information as possible in terms of separation. And when we did that, we plotted those new principal components that we ended up with. We saw that the grass samples were projected down to this right part of the graph, whereas other samples were projected to another part of the graph. And since we could easily separate these ones from the other ones in the 2-dimensional space, we should be able to do it in the 174-dimensional space as well, because I mean, going from this high dimension to the low dimension means we're removing information, and since we can do it with less information, we should be able to do it with the more information as well. So that was, yep, absolutely.
What do you mean by features? Is that
So features is like a variable, like when we have
amplitude and time?
Yeah, so we have a total of 174 features, and that's basically, once we go into the modeling phase, then we have this machine learning model that we are using, and then we input like a variable to that. So we have 174 variables, and 28 of those correspond to just looking at what these radar sweeps look like for grass or for some material.
But they are basically amplitudes of the signal.
Yeah, these are amplitudes, yes. Okay. But then we also have estimates of the autocovariance. So that's another feature or variable, if you will. Did it answer the question? Okay. Yes, so we had this good gut feeling that we were going to be able to get some good results out of this. Yeah, as for the modeling part, we used deep learning, and we had a deep neural network with 2 hidden layers and 174 input nodes, and then we had hyperparameter tuning library to optimize these parameters, which ended up with a dropout rate of 14% and 2%, and yeah, so that was kind of decided by the optimization tools. And if we look at the results of how it turned out to be really good results. So here is an example where the radar has traveled across a grass surface, moved over to a gravel surface, and recorded the measurements all the time. And here we've made predictions through that entire journey. And it starts out predicting 1, which corresponds to grass, and then after a while it reaches this transition where it's a bit unclear boundary and starts predicting a bit randomly and being more insecure in its predictions, until it moves over to the gravel surface, where it consistently predicts not grass for a while. And then we have some uncertainties here as well. So to clean this up a bit even more, the predictions, we did median filtering, where we essentially looked at 5 consecutive, I think it was 5 predictions in a row, and we just selected the median of those to be the prediction. So that would mean that if we have 5 samples here, we're going to discard these ones and take one at the top here instead, and we remove the clusters like that. So that gave us a much cleaner graph. So it was, yes. Don't know. It's been so many years since I worked with it, so I'm not sure where the grass was. But there was, I remember there was some kind of unclear boundary here where it moved from grass to gravel. But we could, I think it was like this speed, something like that. It was not very fast. Yeah, exactly. But I remember we had also, so this was a real stitch of surfaces. We had actual grass being adjacent to actual gravel when we recorded, but we also had pure grass measurements and pure gravel measurements that we artificially stitched together, and then we didn't get this unclear boundary. There was like sharp switch. So somewhere around this point, it changed. And I think that's it. I think it's one thing I learned from this project was that you can use radars for much more than just detecting airplanes in the sky. And some other really cool applications of radars is you have like hand gesture recognition. So I know there's people working with earphones, and you can maybe make hand gestures to kind of turn the volume down or up, and you can snap your fingers to have that as a gesture. And it's really cool stuff you can use radars for. And it's also used in geology, where you can use radars pointing in the ground to make as I understand it, kind of like an X-ray of the ground and see what's underneath the surface without digging and interfering with the nature. And also another thing I think is cool, but some people may think is annoying, is that you have the traffic cameras are equipped with both a camera and a radar. So a problem is that if you take a snapshot of every car passing by, you would have GDPR issues, and you don't want to photograph everyone. So what they do is that they have a radar that detects when a person is driving too fast. It activates the camera and it takes a snapshot. So you only take photos of those that are driving too fast. So that's a pretty cool way to use radars as well. That's it. Thank you. Any questions?
I mean, the result you showed from the grass detector was perfect. But
Yeah.
does that happen every time? Can you repeat that?
Yeah. Unfortunately, we had gathered data that we used for training and so, and then we set some other test data aside for evaluating purposes. So it could be that the model has seen grass of the exact same length as I've been trained on some other part of the lawn, but not this particular lawn.
Did you try a different size of the length of the grass as well?
We're hoping to. I know at the end of the thesis, we're going to try it out on a real-world scenario where we would just take the model and the lawnmower and connect everything together and just put it outside and see how it performed live. But we didn't have the time to do that, unfortunately. So it was a bit of a shame.
Yes.
But
Interesting.
yeah, thanks.
I have one as well. Yeah. Oh, sorry. Can we go back to the model?
Mm-hmm.
So how did you decide on the design of the model? How many nodes and so? I can understand the input layer, but the rest, how did you decide? Did you try it out, or how did you do it?
So we did some parameter optimization with some libraries. So that means we pretty much let some automatic tool choose the parameters for us. And I don't remember if that also selected the number of nodes within these layers. I mean, these ones and these ones are set by us, of course. But I'm not sure about these ones, if those were decided by the...
Did you
by
try out, or...
We did try also to
Okay.
evaluate in different settings and so.
Sorry.
And we also tried different kinds of models like LSTMs and convolutional neural networks and all sorts of things. So
yeah, so you had really nice segmentation in the earlier image there. So I wonder, like, do you think there's more that you could extract even more information than just the boundary between grass and gravel? Like, did you consider applications like detecting whether it was a plot of flowers or something like that, where people wanted to keep it? Do you think it would have the power to predict that kind of change?
could be. I mean, I know there's people also working with detecting objects and so. Like if there's some object in front of the lawnmower, like a rock or something, it doesn't want to hit that. So that's also work done with that. So I think it's of course possible, but they would probably take another approach than we have done and focusing on that part. So it's yeah, you cannot you make one model that does something, and in this case predicting the surfaces. But I think it's of course should be possible to do use radar to detect objects as well, if that's what you're asking.
Yeah. I think another question I had was like, as a layman, you would assume that the simplest way to do this would just be to use a camera and then use object detection,
Yes.
like with the image algorithms. And what's the, like, is there a benefit to using the radar in this case? Or?
Yeah, it's few benefits. So first of all, if you mow your lawn overnight, you wouldn't be able to use a camera because it's dark. So radar works in any lighting, and also with you can also hide the radar within the plastic. So it goes through the plastic and isn't interfering by that. But a camera would also, if you would go on daylight, maybe it's raining and the rain is going to distort the camera. So radar is less sensitive to those kinds of conditions. So that's one benefit with radar. But a good point otherwise.
Yeah, I was just curious what the motivation was to use neural nets for this problem. I guess there's a lot of stuff that preceded it, SVMs and things like that, or is there reason to believe they wouldn't perform as well? Or?
We tried that as well to do with, I know SVMs we tried, and logistic regression I think as well, and they performed quite well as well. But I think it was that the neural networks had this little extra in the end, so we decided to go with that as our final approach.
Okay, I have to ask.
Yes.
Did you try to just use image recognition, like the stupid approach, so to say, without any feature engineering, just to compare, like,
You
how
mean
much it impacted?
image recognition of these
Yes, of the
2D matrices?
yes,
You mean, we did use.
or 3D, if you have 3D, perhaps.
Yeah, I know we did use convolutional neural networks, so I guess that's
Yeah,
somewhat.
but I meant on that raw data, just to compare, like, how did the feature engineering impact the end result?
Okay, you mean if you would do without any feature engineering at all and compare the
Yeah.
results, or we did try to different combinations of features at least, and one of those combinations was to just include the sweeps, a bit pre-processing with like averaging to remove noise and so, and we got quite good accuracy on that as well. So then we're pretty much looking at the characteristics of these curves, I guess. So that did perform quite well, but we significantly increased, I think, by 5 percentage points the accuracy by introducing
expect.
autocovariance.
It's to be better, but
Mm.
it's interesting to compare.
Yeah, definitely.
So I assume that you had the radar pointing, I guess, in the same direction all the time, or
Actually, now that I think about it, we had 2 radars actually. One was pointing straight downwards at the front of the lawnmower, and one was slightly tilted, I think 30 degrees forward to be able to look a bit ahead. And the reason for that was that if we would have a flat surface like tiles, we were thinking that maybe the reflectors were going to go like away like that, whereas for grass it would be scattered at all sorts of places, so some of it would return to the radar. And then this one has an additional radar as well to capture things from a different angle.
yeah, because I know that like if you point the radar in different direction, that you can get significantly different data depending
Yes.
on how things
Yes,
scatter. And
absolutely.
So on.
So we did for two different fixed angles, one flat down and one slightly forward. Yes, go ahead.
Sorry. Like this was. Does it matter if you hit the line, the border, straight on, or head on, or from the side?
What do you mean by the border?
Like the gravel border.
Yeah.
Like I don't know. How does the radar work? Does it Is it very?
Okay, so it's you mean how it works like physically?
Yeah, exactly.
So it's so the radar is actually not just looking straight down. It's actually looking like in a cone like that. So even if we're at the borders here, say, and the lawnmower is here, maybe it's gonna see part of the border right away. So it's gonna be like a blend of grass and the other material at some point until it fully goes over to one surface. And that's why we saw this like unclear transition, because it's kind of a mixture of materials. Right.
Thanks for a great presentation.
Thanks to you too.